Hello guys, today we will learn the boot circuit for the iPhone 11 Pro. So first, let's have a look about the related components on the motherboard. The boot process is CPU extract data from NAND flash chip, then get it into the iOS system. So the main chips for the boot circuit is the CPU and the NAND flash chip. And also, if we want these two chips to work, we need to get some powers. So the power is mainly come from the PMU and this boost IC. And the source of the power is actually come from the battery. So this battery connector makes it possible the connection between the motherboard and the battery. So the 5 chips, they are mainly related with the boot circuit. So let's come to see the working process of this boot circuit. And as we know, the 2 battery connectors on the iPhone 11 Pro. One is mainly related with charging circuit. So for this connector which mainly related with charging, we will introduce in future courses. This orange highlighted part, we can ignore it first. So let's come to see the details of the working process. And the boot circuit for the iPhone 11 Pro is just similar as the iPhone 10 or iPhone 7 we have learned in the previous courses. It looks a little bit complex, but we can separate this process into 4 stages. Let's a brief summary first. The first stage is the PMU chip should be standby to work. And the second stage is the trigger. We need to press the power button to trigger the booting process. And the third stage, CPU should be standby. Just like PMU, CPU standby conditions also including the power, clock, or reset, something like that. So this is the third stage. The fourth stage is CPU extract data like the iOS system from NAND flash chip. So this is a brief summary. And for each stage, there's also some details. So let's come to see the details. The first stage is the PMU should be standby to work. So if we want the PMU to standby to work, the first condition is the powers. And here is a little bit different. For iPhone 11 Pro circuit, the PPVD main will be outputted from the battery connector directly. Okay, and this voltage will be outputted to many components at the same time. Here, for the boot related circuit, we will just draw the PMU and the boost IC for your reference. So this voltage will be outputted and sent to the boost IC and the PMU at the same time. And when the boost IC receives the PPVDD main, it will inner processing and output the voltage as a PPVDD boost to PMU. Okay, so let's come back to the PMU. Now the PMU with PPVDD main and PPVDD boost, the 2 powers supplied. So the first condition for PMU is fulfilled. Then the second step, a PP1 volt 8 always will be generated at this rail. As we can see, the yellow highlighted rail, they will always have a 1.8 voltage. The third condition for PMU to work is to generate the frequency to work, and the frequency is provided by the Y3000 by this crystal, and the frequency is 32.768 kHz. Okay, so 3 conditions: the 2 powers, the PP1 volt always, and the crystal generate this clock. Then with the 3 conditions fulfilled, PMU will be standby to work. Okay, so this is the first stage. The second stage is we press power button to trigger and start up the system. Let's see this rail. As we can see, there's PP1 volt always, and this voltage, after this inner resistor, it will change the name as IO button side. So we can see this is strop connector which related with a power button. And before we press the power button, this rail is open. So the voltage that we can measure on here is 1.8 volt. Okay, so here's this voltage before we press the power button. It's 1.8 volt. And when we press down the power button, just like this, then we can see these 2 points are connected, so the voltage will be grounded. and drop to 0 volt. Press and hold the power button for a few seconds, then release the power button. And the moment when we release the power button, the voltage will up to 1.8 volt. So this kind of voltage change is just like a trigger signal. So when PMU receives this kind of voltage change, the trigger signal, it will start the third stage to output powers for the CPU and the NAND flash chip. And let's zoom in to have a look. There's so many powers it will be outputted to the CPU and sent out to PMU itself. Also, the some voltage will be outputted to the NAND flash chip and other chips at the same time. Okay, so the third stage, let's see details how the PMU output powers to CPU and NAND flash chip. The total 19 bucks for CPU and the PMU itself. So let's see details of the 19 buck power supplies. The first is PP CPU P core. We can see the voltage range and the maximum current. Okay, the second rail is PP GPU for the graphic processing unit. There's also some voltage range and the current, which we can find from the schematics. And the third power for the CPU is PP SoC S1. Okay, and for the rest we can go through very fast. PP 1 volt 8 S2, PP 1 volt 8 IO, and this voltage it will be also provided to the NAND flash chip. This one is PP 1 volt 1 S2, PP DISP S1. This is related with display, and the PP 0 volt VDD low, PP 0 volt SoC fixed, PP SRAM S1, PP AVE S1, PP DCS S1, and PP 0 volt 6 VDDQL S1. Okay, the rest one PP CPU E core, and E here might means efficient core. Okay, the last two PP 1 volt 2 SoC and PP 3 volt 3 USB. So here's the power supply for the CPU, totally around 16 rails. And for each rail, there are also many small components like the inductor, capacitor, or resistor included. So you can refer this block diagram to have a look first. And if you want to see the details, you may need to refer the bitmap, because the space here is limited, so some components are not drawn here. Then let's come to see the rest rails. There also 3 voltage will be outputted to PMU to power itself. One is PP 1 volt 2 S4, and the second one PP 0 volt S1. The third one is PP 1 volt 8 S4. Also, as we mentioned, PMU is just like the heart of the power system, so it will not only provide power for the CPU and itself. And here let's come to see the power supply for the NAND flash chip. These 3 sets of voltage will be outputted to the NAND chip. One is PP 1 volt 8 IO, and second one is PP 0 volt 9 NAND. The third one is PP 2 volt 63 NAND. Compared with iPhone 10, the third voltage gets lower. I think it's get optimized to save the energy. So by now the power outputted from PMU is finished. Then let's come to the CPU working condition. With the power supply fulfilled, then the CPU also needs some clock signal. Here the clock for the CPU is generated by the Y1000 crystal. As we can see the number and the frequency is a little bit different from the one which related with PMU. Okay, this one mainly works with PMU, and this one is mainly work with CPU, and this one Y1000 is mainly work with CPU. Then we also need a reset signal outputted from PMU to CPU. So with the power, clock, and the reset fulfilled, then the fourth stage, the CPU will start to extract data from NAND flash chip through the PCIe interface. So by now the boot process is almost finished, but there's still some other rails we did not mention. Let's have a look. SPMI bus, and SPMI is short for Supply Power Management Interface. So the use of this interface is to ensure PMU providing powers to the CPU the NAND flash chip, and other chips continuously. Also, we have a boost IC. This one is mainly used for providing the boost voltage. Another use of this chip is when the voltage is lower than 3.4 volt. An enable signal will be outputted from PMU to the boost IC. So when the boost IC receives this enable signal, let's zoom in to have a look. When the signal gets received, it will boost the voltage to 3.4 volt. As we can see the quote from schematic, when VDD main is less than 3.4 volt, it will boost the voltage to 3.4 volt. Otherwise, it will track the VDD main. So with this kind of function, the boost IC can make our phone works with longer time. So this is the working process for the boost circuit. And in the next lesson, we'll learn the troubleshooting process for this circuit. Thanks and have a nice day.